Hello, Charlie.
We've had summer today.
We've had summer today, and a couple of weeks ago I was doing um, current events, and right beforehand we had the Zoom outage. Kind of looking out the window now and hoping we are able to get through this little presentation without some kind of a disaster. If it happens, I'm going to definitely feel a little paranoid.
Well, I'm sure it will work well. Fingers crossed, always.
Hello, I was listening in earlier. Is someone having a pretty good storm? Worried about flooding?
No, I'm just saying that a couple of weeks ago I did current events. I was the moderator, and that was the day that we had the Zoom outage. And so just a half an hour beforehand, we're rushing around trying to set up an alternative means. And now there's a severe thunderstorm watch, and it's suddenly gotten very dark, and I'm feeling like I have bad karma or something, but I hope not. But we'll wait another minute for other people to join, since we don't have to be too strict. We don't have to have our quiz at the end. Okay, well, I think I'll get started. So hello, everyone. Um, Welcome to Imagining the Universe. And tonight, we're going to talk first of all, what's up in the night sky this month. And then we'll talk a little bit about supernovae, which are very powerful and catastrophic explosions that take place at the end of a star's life or some stars' lives. And we'll talk about how we discover them. And we'll talk a little bit about the history of observing supernovae and why it's actually not that easy to find ones that are nearby to us, but yet we observe hundreds to thousands of them every year. And starting at the end of this year, there's a program, as I'll talk about, which will discover 1,000 supernovae every night. So, first of all, just astronomical highlights. We just passed the new moon. So obviously we're not going to be able to look outside at clear skies tonight, but maybe tomorrow night, if you look out 45 minutes after sunset, which is you should start looking after 8:30 in the evening. If it's clear tomorrow, you'll find the crescent moon, and above that, the Pleiades or the Seven Sisters, and a star called Aldebaran. And above that will be Jupiter. So you could look for those. This is what we would be seeing tonight. This will be tomorrow night, the 30th. So maybe if it's clear, you can look for that. The next full moon is on May 12th. So this is actually a good time to go out, a time of the month to go out in the evening and look. You'll see the crescent moon get bigger and bigger and higher in the sky. The full moon in May is called the flower moon. In terms of astronomical observations of the planets, we could see a bunch of them, but none of them, well, I guess Jupiter is pretty prominent, but most of them are not that easy to see this month. So here's a little diagram that shows coming up in the beginning of May, 1 hour after sunset. If you look up in the sky towards the west, halfway up, you'll see on the 3rd of May, the moon and Mars. On the 1st of May, the moon is down here and Mars is up there. So again, you can use this kind of diagram to figure out where to look for Mars, the red planet. Mars was very bright a few months ago, but it has now moved further away from us in its orbit, and so it's not as bright as it was. If you're an early morning person and you get up 30 minutes before sunrise on the 3rd of May, you'll be able to see Venus easily because Venus is bright. And off to the right of it will be Saturn, and then very, very low on the horizon, looking straight east, you might catch a glimpse of Mercury, but Mercury is really hard to see because it's pretty close to the sun, and the sun would be coming up by the time Mercury got higher up in the sky. Okay, so today what I want to talk about is supernova. A supernova is an object which, before it brightens enormously, is hardly noticeable. And yet, if you looked at this particular part of the sky, 2 hours later, it looked like this. So a supernova, a nova stands for new star. In other words, a star might not have been there the night before to the naked eye. Suddenly becomes very bright, and those were dubbed novae, or nova, a nova. And supernova are an exceptional class of suddenly appearing stars, where the star brightens by perhaps a factor of 100,000. So here's a little example of an image of a galaxy that's about 30 million light years away from us. And there are 2 images. And if you stare at them carefully, you should be able to notice that there's an object in the right image which is not visible in the left image. So what you're seeing here is a spiral galaxy. Here's the nucleus of the galaxy. Here are the spiral arms, and you see they look the same. What you're looking for is a star that appears on the right image and not in the left one. And if you haven't picked it out by looking very carefully, here it is.
I can't get this to work.
There it is. Everybody see that if I turn that off? So in fact, this is a supernova that was discovered in this galaxy. And so how are supernovae discovered in distant galaxies? People take multiple images and then they look for objects that weren't there and suddenly are there. Here are some other examples. These are distant supernovae in galaxies that are much further away that were discovered by the Hubble Space Telescope. On the bottom panel, you see an image taken before there was a supernova. And then Hubble went back for one reason or another and looked at the same object. And when they compared the images taken earlier and later, they noticed that there was a very bright object associated with the galaxy that hadn't been there in the previous image. So what is then a supernova? It's an object, a star, which shows a sudden brightness by a factor of 100,000. And this is caused by a catastrophic explosion of a very massive star during the last moments of its thermonuclear burning phase. Sometimes supernovae are so bright that they're visible for a period of weeks and months during the daytime. Those would only be ones which were very close to us, but we'll talk about the ones that have been observed historically in a couple of minutes. Supernovae are important to our understanding of the universe for a variety of reasons. Philosophically, the observation by Kepler and Tycho Brahe, in fact, historical astronomers, that the heavens weren't perfect, that the heavens were dynamic, that things in the heavens could appear and disappear, was a philosophical argument for the wonderment of the thing they called the universe. Very important to us as human beings, a carbon-based species, it's in these catastrophic explosions that the heaviest elements, all the parts of our body, are actually created in the thermonuclear explosion that occurs. We'll also see that we can detect neutrinos from supernova 1987A, a particular supernova that we'll take a look at. And the fact that we detected neutrinos, which are very low mass particles, traveling, billions of them are traveling through us at any time, although we don't feel them. The fact that we were able to detect them validated our understanding of what causes a supernova. Supernova explosions sometimes lead to the formation of black holes, which will be the subject of another talk sometime in the future. And supernovae also turn out to be what we call standard candles. They all have the same maximum brightness. And so if we can observe them at different distances and they have the same brightness, then their apparent brightness tells us how far away they are. And that produced the first evidence for dark energy, another subject we'll have to talk about someday. Okay, so in order to understand that a supernova is a catastrophic explosion, we have to remember what keeps a star up. What keeps it from collapsing under its own gravity? Because the mass of the star itself is attractive. The gravitational force tries to pull the material towards the center. What's holding a star up is the outward pressure of the gas that is heated by the thermonuclear reactions taking place in the center of the star. And so we have a star, a simple diagram of a star. The gravity is pulling inward. In the core of the star, for the sun, it's about the inner quarter of the sun. There are thermonuclear reactions going on, which heat up the outer layers, which pushes against the gravity and keeps the star from collapsing. The sun's been in that state for about 4.5 billion years. It's going to be like that for another 4.5 billion years. And if eventually the sun stops burning, something bad will happen to it. However, let me make it clear right away, the sun will not become a supernova because it is not massive enough to undergo that catastrophic explosion. High mass stars, and that's what are important in the context of supernovae, are much more interesting than what we call low mass stars like the sun, because their centers are much hotter and denser. They use up their fuel. They burn ferociously and they use up their fuel very fast. They have much more energetic nuclear reactions that take place. They live short periods of time relative to a star like the sun. So the sun's total lifetime will be about 10 billion years. It was formed about 4.5 billion years ago, but a much higher mass star might only live millions of years. And so high mass stars, there have been many, 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 many generations of them during the 13.6 billion years of the history of the universe. As I said before, they also have much more complicated nuclear reactions, which involve heavier and heavier elements, so that the sun is right now is burning hydrogen into helium, and so it's making helium, but it's not making anything else. In the future, the sun may produce some carbon, oxygen, and nitrogen, but the really heavy stuff requires these high mass stars to make them. And then the other thing that's important is they undergo high mass stars can undergo catastrophic explosions like supernovae, whereas the sun won't undergo that kind of a catastrophic explosion. It will blow out its other layers in what we call a planetary nebula, which I talked about in December.
Martha, can I just bug in for a second? My
Sure.
daughter, my daughter just called with a warning that there is a possibility of a tornado. And it is suggested that we all go into our basements for the next 10 minutes.
Okay, then why don't we do that? We'll come back at 9:25, 9:30. We'll keep an eye on it. That's a good idea. Thank you. I'll just leave us connected. If not, I'll connect back up later.
Martha, this is Betsy. I'm also on Tompkins Siren. A tornado warning for southeastern Seneca County, southwestern Cayuga County, and north central Tompkins County until 7:15. So take cover now. Blah blah blah.
Well, I don't want to put anyone in a bad position. So why don't we come back in 10 minutes?
Okie doke.
Okay, well, I think hopefully it's passed. It's still raining at my house, but I don't hear a lot of thunder.
No, that stopped here.
Yeah. Okay, so let's pick up where we left off. So as I was saying before, the high mass stars are more interesting to us in many respects. And in particular, they're the ones that make the supernova. So what happens in the supernova is that, as I said before, we have to have this balance in order to hold the star up between the thermonuclear reaction heating up the gas and pushing outward, and the gravity which is pulling in. And in a high mass star, at the very end of its life, it configures itself. So this is just showing you the inner part.
She's talking again.
Not the whole part of the star. We have
Can't hear
layers
anything.
of we have layers where there's hydrogen, helium, carbon, neon, oxygen, and silicon. And inside of that, there's a core which is made out of iron. In order to make iron burn, you would need an enormous additional amount of energy. And so the burning stops with this iron core. There's burning that's continuing to go on in some of the layers above it, but not in the core itself. And when that happens, the star very quickly actually reaches the point where gravity wins and the inner part of the star implodes. That also causes a series of reactions. So within the period of about 0.1 seconds, a tenth of a second, the core of the star collapses. That core could be more massive than the sun. Within about half a second, we believe that a burst of neutrinos is emitted. And so one of our predictions was that we should be able to detect neutrinos. As I said before, we have detected neutrinos from a supernova. About 2 hours after that, material is falling in, but it kind of bounces off the central layers and pushes outward. Additionally, all of the radiation and the heat that's been generated reaches the surface of the star as it's ejected, and the star brightens by a factor of 100 million. So in a very, very short period of time, you have this catastrophic implosion followed by an explosion. And then over the period of months, we see an expanding remnant as the outer layers of the star are blown off, and those layers emit X-rays, radio, visible light, and then over some period of time, it actually starts to fade. Additionally, if we are able to measure the chemical composition of what's in those layers, it's all of the heavy stuff that was created in that 0.1 second of the core collapse and the catastrophic explosion. So here's an example. I showed this image before. I think they were flipped. This is a supernova called 1987A because it was discovered in January of 1987, was the first supernova discovered, so it's called A. It actually was bright enough that it was discovered by an astronomer at the Cerro Inter-American Observatory who went outside and looked up in the sky and said, wait a minute, that star wasn't there before. He was very used to observing the sky, and he noticed that if you look in a portion of what's called the Large Magellanic Cloud, it would have looked like this. Instead, it looked like that. The object, the Large Magellanic Cloud, is a galaxy. It's a dwarf galaxy compared to our own. It's about 160,000 light years away, which means that the supernova actually took place 160,000 years ago, but the light took that long to reach us. Then physicists who study neutrinos, which are these almost massless particles that do not interact with normal matter, were able to look at some neutrino detectors, one in Japan, one in Ohio, and one in Russia, And they actually realized that they detected an excess, a small number of neutrinos, extra neutrinos, like 11 in Japan, 8 in Ohio, and 5 in Russia. And that they were coincident with being 2 hours before the brightening of the star is observed in the optical with the naked eye. So that was a confirmation of our idea that you get the implosion and you get the production of neutrinos. Oops. Now, what will be very important to us is not necessarily the explosive brightening of the star, which, as we'll see, lasts a period of months. But what we also see are the remnants of the star having been blown out, and we call those supernova remnants. And we can observe them at optical, radio, and X-ray wavelengths, and they look like this. So, for example, this is what we call a supernova remnant. It can be seen with a relatively small telescope, and we believe that it's associated with a supernova that we'll talk about in a few minutes that was observed in 1006. And here's another supernova remnant. I just show you 2 different ones so that we understand it's the explosion of a star that's then causing its outer layers to expand, so it looks roughly spherical. But you know, real supernovae aren't quite that simple, and they're blowing out into the interstellar medium, and so oftentimes you get more complicated structures. But nonetheless, these are the remnants of the star. All of this stuff was once upon a time in a much smaller volume inside a star. Okay, so again, we've talked a little bit at various times about the fact that we, in fact, are stardust. All of the heavy elements that are in our body, especially things down here like phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and all the other things, they wouldn't be in our bodies if supernovae hadn't gone off before the sun was formed. Remember, the universe is 13.7 billion years old, but the sun is only 4.5 billion years old. And all of those supernovae, of all those stars that only lived millions of years, not billions of years, have polluted the gas clouds out of which the sun eventually formed. So supernovae are very important for producing the heavy elements out of which we are made. And here's the periodic table. The sun is converting hydrogen and it makes helium in the future. After another 4.5 billion years, the sun, or later in its life, it will also make some carbon and oxygen. But all these other things need supernovae to help make them, or massive stars at least. Now, one of the problems, so we can say, okay, we just have to go outside and look at supernovae, but it's really not that easy because there are a lot of other celestial objects, stars, which vary in brightness. And so, in fact, there are lots of different kinds of stars which vary in brightness, so they become brighter and fainter and brighter and fainter and brighter and fainter in a very periodic and repetitive way. Those are called periodic variable stars. One example are the Cepheid variables named after the star Delta Cepheus, and people have observed them for hundreds of years. Supernovae, on the other hand, show a huge increase in brightness by a factor of 100,000 or even more over a period of time. So here, the Cepheid variables vary with periods of days to months. A supernova becomes suddenly bright, and then it becomes fainter over time. And then after some period of months, up to a year, it has gone back and become no longer as bright. So we call how the apparent brightness varies as a function of time the light curve, and supernovae have a very different way of brightening and then fading than other kinds of variable stars. it also will turn out that not all supernovae are the same. And in fact, there are two types in particular, which we cleverly call type 1 and type 2. Astronomers are just so clever with their names, aren't they? So let's also remember that when the star dies at the very end and it collapses and the envelope is blown off, but you have the core remaining, we can end up with a white dwarf, a neutron star, or a black hole, depending on that remnant, as we call it, depending on its mass. The sun is going to become a white dwarf. We know that. Not massive enough to become something else. If the star is a little more massive than a white dwarf, the star can actually collapse and become what we call a neutron star, so that the protons and the electrons in the star get forced together to form neutrons. And it's also possible that if this core is massive enough, maybe like 5 times the mass of the sun, we get a black hole. Subject for another time. What I just want to point out is that white dwarfs are stable, but if something happens to make the white dwarf more massive than it used to be, it can also become a supernova. And that is what we think we see in a number of cases. So we have to remember the sun is a single star, we think, and it has its planets, and everything is hunky-dory and things are quiet. But about half of all stars actually have companions, and those companions are evolving, and some of them can be massive, and when they reach their later stages of life, they expand. And so if you have a white dwarf star, which can only be up to a certain mass, or else if it gets more mass, it can supernova. If there's a companion star, which expands, that some of that outer layer, which used to belong to this star, can fall into this star. Gravity can cause the outer layers of the expanding companion to flow on to the compact remnant, and it's possible that a white dwarf, which was happy to be small, suddenly becomes too massive to remain a white dwarf, and it will also explode as a supernova. And that gives us our 2 kinds of supernova. So we have supernova, the regular supernova. Now, this is another one that's astronomers not being very clever. The kind of supernova that we talked before about a single star with a core collapse, that's a type 2 supernova. And a type 1 supernova is this case where we have a white dwarf which accretes mass from a companion and goes kablooey. These are important. We'll talk about these kind of supernovae when we talk about dark energy. For the purpose of tonight, let's just remember that supernovae are when a star catastrophically explodes. Okay, so let's talk a little bit about early records, because I think this is interesting. And in fact, somebody asked about this before. So have we observed, nowadays we have all these fancy cameras and digital equipment. Have supernova been observed historically? There are several. The part of the problem is, how do you really know that it was a supernova and not a nova or not some other phenomenon when you don't really have any kind of a record? There are several possible appearances of very bright new stars that have been reported, particularly in China, that appear to be supernovae, but in some cases, it's not clear whether they were really supernovae of the other kind of brightening of stars, what we call novae, a smaller degree, which is due to this mass transfer, but not where the stars exploded. However, there are a bunch of cases. So this is a very nice diagram that I found, which summarizes all of the supernovae which also have remnants, and therefore which if you have a supernova, you're going to end up with a remnant. So today we might see the remnant that could be the supernova. And so there are 8 of them, I guess. So 1, 2, 3. Yeah. The first one is called supernova 185 because it was observed in 185 of the current epoch by the Chinese. It was visible in the sky for 6 to 8 months, and there's some evidence of a similar appearance of a bright star by the Romans, although we're not sure. It turns out, from the description of the Chinese, it's in the direction of a supernova remnant that has been observed by X-ray astronomers, and they can actually measure the expansion of the ring of debris and ask, okay, if it's expanding, when was it back on top of itself? And the answer is about 2,000 years ago. So it's believed that this could be a supernova, although, it's not proved because the Chinese records aren't that accurate as to where it was in the sky. The second one, which is debated as to whether it's really true, is there was an appearance of a guest star. Again, sometimes they're called new stars and given the name nova. Sometimes they're called guest stars, stars that appeared and then disappeared. There was one in 393, which was noticed by Chinese astronomers, not recorded anywhere else. There is an X-ray remnant, which this shows a wide field image from the XMM satellite and the Chandra X-ray Observatory, and there is a remnant which appears to be in roughly the same part of the sky. Again, not really totally convincing, but possible. Then we get where a little bit later people are paying more attention. There are better records. There was one in 1006, which was observed extensively in China and Japan, and also recorded in Europe and the Arab regions. It was 16 times brighter than Venus at its maximum brightness, and this shows you the remnant. We can't see the star anymore. It's somewhere buried in there, but we do see the supernova remnant. Again, if you measure the expansion speed of the gas and asked how long ago would it have been much smaller, it's roughly 1,000 years. The next one was in 1054 AD. Here is the supernova remnant. It's called the Crab Nebula. It's visible with a relatively small telescope. It was observed extensively in China and Japan, possibly Turkey, but it's not noted in European literature. And there are disputed claims as to whether it appears in the cave paintings in Chaco Canyon. What's also very interesting is in the center of this remnant, there is a radio pulsar rapidly rotating neutron star, which is what you'd expect to find in the center of a supernova remnant. It's quite nearby. Another one in 1181, which is recorded extensively in China and Japan, and it is also very close to a supernova remnant, which also has a neutron star radio pulsar in the center of it. So we're pretty sure this one, pretty sure of this one. Then it becomes more interesting. We travel forward a little bit, and now we're getting to what you might call the beginnings of modern astronomy. So Tycho Brahe lived from 1546 to 1601. He was perhaps the greatest observer of all time. I think that's all he did. And even though he was in Denmark, the skies were pretty clear for him, at least part of the time. And he kept meticulous records of observations of planetary motions. In fact, it's his observations that led to Copernicus to propose his understanding of the universe, and also Kepler to revise the idea of elliptical orbits. And in 1572, he observed a supernova. He was very lucky. So let's think it's recorded in this book, which he published. in which he draws out the constellation. And he was also talking philosophically about the idea that the fixed stars could change, which philosophically was revolutionary for the time. So let's just think about what he saw. The idea is that it was in the near the constellation of Cassiopeia. And so he was used to seeing the constellation of Cassiopeia, which is visible in Ithaca, especially in the fall. So all of a sudden, he would have expected, he would have known all of these stars, but suddenly he saw that. And it would have appeared in the course of a night. And then over a period of time, it's believed it was visible also during the daytime, and then over a period of the next month, it fades and then it goes away. It today is identified as a tiny little star. This is a HST image of the star, which is also seen in this, the glowing part here, the nebulous part is from the Chandra X-ray Observatory. Again, there's a supernova remnant that we see that we can trace back to this star. Okay, who's the other person who comes along after Tycho? Kepler, 1604. So, 20, 30 years later, Kepler observes a supernova. Again, nowadays we see the supernova remnant, and again, we measure the expansion velocity, we put it back, we figure out that it's only 500 years old. In fact, we can take the measurements because various astronomers, Kepler didn't find this supernova, but he did observe it. It was also observed in China and Korea. It was discovered in Europe as far as records show. But here you see it brightened and then it faded over time. And there are both European and Korean observations that relative to other stars show that they're describing the same object. Okay, so now here's an interesting question. It's hard to predict the appearance of a supernova, but new ones do appear, and we are discovering them, and we'll talk about this at the very end. We're all set up to discover 1009. But based on our observations in supernovae and other objects, and so you see in these little diagrams, they're inset arrows which point out the difference between 2022 and 2023. So here it was when there was the supernova, and a year later the supernova is gone. In the other case, the supernovas appear in one image and not the other. We estimate that a supernova should occur in a galaxy like the Milky Way every 50 to 100 years. But why haven't we observed any in the Milky Way since 1604? Well, that's because the Milky Way is kind of a mess. In fact, in between the stars and the Milky Way, there's a lot of interstellar dust. And the dust blocks out the starlight that you observe at optical wavelengths and causes us not to be able to see very far into the Milky Way. So in fact, around the sun, we only see, we're embedded, the sun is embedded in the Milky Way's disk, quite far out from the center, and we only are able to see about 6,000 light years away from us. So we can only see at optical wavelengths this much of the Milky Way, not very much. Whereas the Milky Way extends 100,000 light years across. And just to, again, further emphasize this, here are two images. Here's one of the pillars of creation, the Eagle Nebula, taken with HST. And here's an image of the same region taken with HST, but in the infrared. And you can see, you can look through the pillars and you can look through the dust and gas and see all these other stars, which are completely hidden from us at optical wavelengths. So here's the center of the Milky Way Galaxy with an optical camera. And here's the center of the Milky Way Galaxy with an infrared camera. And so I put those two on top of one another, and with an optical telescope, you cannot see the center of the Milky Way because it's about 25,000 light years away, and we only see within 6,000. On the other hand, with an infrared telescope, you see the starlight in the center, and you also see all this dust. So, because we live in the center of the Milky Way, then the Milky Way is a mess. We can't see all the supernovae that occur. And so Tycho Brahe and Kepler were really, really lucky that they actually got to observe supernovae. Okay, so how should we go about discovering supernovae? Because they're really interesting. We want to know more about them. What you have to do is you can't just stare at one spot in the sky and expect the supernova is going to go off there. You have to look all over the sky because you don't know when they're going to go off. And so they will be discovered by surveys of the sky, which make repeated observations of parts of the sky over and over and over again, and then look for objects that vary in brightness in a characteristic way. We have to be able to distinguish the supernovae from all of the other objects that vary. And so the first thing we want to do is we want to be able to look over a large area of the sky at once. That's called having a large field of view. So let me just remind you what I mean by field of view, wide angle lens, field of view. Here's a nice picture of the Orion Nebula and the Horsehead Nebula and the Flame Nebula. Taken over a region of the sky of about 6 degrees by 4 degrees. Keep in mind this dimension about 4 degrees. Here's the size of the moon. When you observe with the Hubble Space Telescope, or JWST, you observe a teeny, 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 tiny, tiny part of the sky. But if we were to do that, it would take forever to map the whole sky, and then we'd have to go do it again. It just wouldn't work. We do discover supernovae with telescopes like Hubble and whatnot, but it's normally by accident. Someone is looking for a galaxy and poof, there's a supernova that goes off in that galaxy, but not in the other 100 or 10,000 that are in the same frame. So if we want to search for supernovae, we need a camera with a large field of view. We also want to be able to look at different wavelengths at closely spaced times, because again, that helps us to distinguish supernovae from other objects. And we also need powerful computers who are going to take hundreds of millions of images and compare them quickly, so that you can see the supernova, because once you discover it, you want to observe it within the next days, because that's when it's changing in brightness so much. So we're building such a telescope. It's called the Rubin Observatory. It's located in Chile, at Cerro Pachon down here. The telescope, the FEAST telescope that we at Cornell are building, is up here near Alma. This is further south at Cerro Pachon. And it is going to be in operation starting at the end of this year and will survey the sky for about 10 years. It has an 8.4 meter diameter primary mirror telescope, and it will look over a field of view of 3.5 degrees. So in the image I showed you before, I pointed out 4 degrees. Its camera is almost taking a snapshot of a 3.5 degree circle every time it takes an image. It's actually very impressive. It will cover about 10 square degrees, which is 3,000 times the area of a single Hubble Space Telescope image. It has a filter wheel on it, which has 6 different filters in the optical portion of the spectrum, going from red to green to violet. And so it's going to do a 10-year repeated imaging of the sky in the 6 optical filters. It will revisit some parts of the sky every night, some parts of the sky every 2 or 3 days, some parts of the sky once a week, et cetera, to try to maximize its ability to discover objects that either move, things like asteroids or comets, or objects which turn on and off. It expects to detect 100,000 things that change in brightness every night. And then it has to figure out which of the 100,000 events every night is a supernova, but it expects about 1,000 supernova per night. Not in the Milky Way, in galaxies throughout the universe. So there's one last thing that we might ask, and that is, are there any stars that we might expect to supernovae? And we do understand what happens at the end stages of life of a massive star. And there are a number of luminous, massive, peculiar, weird, variable stars that are believed to be in their late stages of evolution. And one of them is a star called Betelgeuse, which is one of the stars in the constellation of Orion. And this little diagram just shows you that's the size of the sun. Here's Aldebaran. This is a star to the up in this direction from Orion. Here's Rigel, the bluer star in Orion. Here's Sirius, the dog star. And here's Betelgeuse. It's what we call a red supergiant star. It's about 10 times as massive as the sun. What's interesting about it is during the period from 2019 to 2020, and it's still doing some weird things occasionally now, it was actually seen to change in size. It is such a big star and relatively close by that using multiple optical telescopes and interferometer, astronomers have been actually able to take an image of it, to actually resolve it from a point source. And you can see here how it has changed in brightness. Over the period of 5 months in 2019, 2020, it dimmed to be only half as bright as it should have been. And what we understood was that, again, it's beginning to become unstable. It's not quite ready to blow up, but it's beginning to become unstable. And we believe that it gave off a huge plume of gas, but not in a completely symmetric way. There was more dust on one side of one part of the star than another one. But it leads us to believe that it will probably explode sometime in the not too distant future, where that number is about 100,000 years. So don't worry about it. We're probably not going to see it. And this is an artist's rendition of what happened. There was some of the material in the outer part of the star blew off, but it wasn't a supernova yet. But it's getting towards the phase that maybe in 100,000 years it will become a supernova. So then we can ask the question, should we worry about a supernova going off near us? And here are a couple of HST images of a few other weird looking stars, which are massive and bright and are also in their later phases. And so I'm pleased to tell you that we can calculate when a star supernovas, the material is blown off. There's a lot of very high energy radiation and particles, gamma rays, X-rays that are also emitted. And it would probably not be nice to be near a supernova. But in fact, if a supernova would have to be really quite close to us in order to do damage to life on Earth, probably of order 50 to 100 light years. And the good news is there are no stars that close that are massive enough for us to expect that they would supernovae anytime in the next 10 billion years. So we don't really have to worry about it. On the other hand, if some of these nearby stars were to supernova, they would become really bright and would be visible in the night, in the daytime sky. So anyway, that's what I had to say. I'll take questions, and I'll see you on May 27th. But for now, I'll take questions in the chat, or you can raise your hand. Anybody have any questions? They're not as exciting as tornado warnings, but and we don't really have to worry about them, but it would actually be kind of cool to see one. Alan?
Um, so how confident are we that novae, sorry, I'm mispronouncing it, in the early universe would have the same kind of, like, approximately the same kind of maximum brightness than ones that we see
That-
nowadays?
That is a really good question. And of course, that was a fundamental question about the discovery of dark energy, which depended on the fact that the distant supernovae had the same maximum brightness as the nearby supernovae. And that also, when you observe a supernova, even though in the Milky Way, dust in the Milky Way is a really big problem for observing supernova because we can't see very far. In the distant universe, we do have to worry about dust in the other galaxies. And so we have to make a correction for that. But if the supernova is on the outer part of the galaxy, there's not much dust and it's okay. So we have to throw out some of the supernovae because we don't know how to correct for the dust. But also, in the early universe, there wasn't as much carbon, nitrogen, and oxygen around as there is today. And so there has been a question, if would a supernova in a star that was formed earlier in the universe that didn't have carbon, nitrogen, and oxygen, would it explode and have the same maximum brightness as one in the nearby universe where you already have a lot of carbon and nitrogen and oxygen, and you have some silicon and all the other stuff that wasn't there in the earlier days? And that probably gives us a slight difference, but it is not enough to do away with the idea of dark energy. And again, that's when you send the theoretical nuclear astrophysicists off into the room to figure out what kind of thermonuclear reactions take place in a phase in which the nuclear reactions are taking place with less carbon, nitrogen, and oxygen. But it is something that we do worry about. And in fact, there's something that, another topic for another future lesson is this idea that there's some kind of a cosmic conundrum that the supernova distances the expansion rate of the universe you get from supernova is not quite the same as the expansion rate of the universe you get from other measurements. And it's called the Hubble tension. And the different measurements that you make don't get quite the same answer. They're not really very far off, but the people who do supernovae, they say our measurements are perfect. And the people who do Cepheid variables or some other measurements say our measurements are perfect, but they don't agree quite. And it may have to do with some of these subtle details that we don't understand completely, but that's what keeps astronomers busy.
Martha?
Oh,
This
Betsy.
this is Betsy. Not a scientific question, but a practical question. All of this defunding that's going on and the talk about worse. What can you say what that will do to some of these programs and buildings and?
Yeah, well, the fact is that Rubin is already paid for, and in fact, the camera's been installed and they're checking it out right now. And they've got first light, they've got first images. They're hoping to start the survey but before the end of the year. So there may be no astronomers employed who can look at the data or reduce the data, and they need these, it's the computer facilities that are enormous to go through all of these images. I mean, they're taking images every 3 to 5 seconds, and then they switch to another filter, and then after 15 seconds, they move to a different part of the sky, and they have gigapixels in their cameras, and they have to compare everything. They need a lot of computer power, so we worry about that. What I didn't mention is there is another telescope that is, it's a space telescope. It's called the Nancy Grace Roman telescope, the Roman telescope. And it's supposed to be launched in 2026. It's all ready to go. It's been paid for. And in the president's budget, it's canceled. Why you would build a telescope and keep it on the ground is another question. So that's kind of depressing. If right at the moment, the president's budget cuts the NASA budget in half, but it refocuses the NASA budget towards going to Mars. And so the research budget gets cut by 2/3. And they cancel Roman. And the only telescopes they keep going, they cancel Chandra. They cancel involvement in XMM. And they only keep Hubble and JWST. The National Science Foundation gets cut 50%. I think the only telescope that might be left going is Rubin. They're not going to stop Rubin right now because they've just finished it. And so it could be really bad. But let's talk about galaxies and supernova instead. That's why we're not watching CNN tonight. Okay. So there's a question that Robbie put in. Are stars forming at a rate similar to the rate of the explosions of the supernovae? No, there are lots and lots more stars that are being formed, but they're not massive enough to become supernovae. And also, there were a lot more stars in general, both massive ones and low mass ones, formed earlier in the universe than there are being formed today. The young universe was very fertile and produced a lot more stars in a year than the mature universe is producing 13.7 billion years later. And as a matter of fact, that's going to be my talk for next month. I want to talk about how JWST has completely changed our understanding of how galaxies and stars formed in the early universe. Because we went in from Hubble, we had an idea of how stars and galaxies formed in the early universe, and this was going to be fine, and JWST was going to confirm this, and JWST has told us that we didn't know anything. Which again is, it's good for the young astronomers.
Do you have predictions? What else will fall by the wayside? Meaning that what you think is right, and I mean, is there a
Well,
list
it's raised a whole lot of questions that we still can't answer. But the fact is that we thought that we really don't understand how stars formed early on. And we're more confused about how supermassive black holes formed and how massive galaxies formed in the early universe, because there are way too many galaxies, massive galaxies and massive supermassive black holes in the early universe than we had thought. And we don't know how they formed, because they had to have formed in a really short period of time, and they weren't supposed to do that. So, and of course, JWST does many, many other things, which are wonderful and surprising, and so, you know, we'll have to talk about exoplanets sometimes too, which is not my field, but it's pretty interesting. But you see, I guess I'll have to, I'm only slated to do one more talk, but I guess I'll have to do more than that.
When are you going off to Italy?
Well, so I'm going off to Italy on the 28th of May, and I'll be back on the 19th of June. And I didn't want to plan anything till June until I got it organized as to when I was going to Italy, and getting things organized with my in-laws is always fun. But my mother-in-law's 102. She's waiting for me.
Wow. What is JWST that you talk about? It's a telescope or a,
Yeah, it's the 6.5-meter telescope that was launched a few years ago. It's the infrared version of Hubble, and it's a bigger telescope. And
Okay.
so right now we have Hubble, which is old, which celebrated its 35th birthday
wow.
this week. I always remember when it celebrated its birthday because it was launched on my birthday. However, I am more than 35. I have to admit it to you all, but that's beside the point. And then JWST was just launched a couple of 3 years ago, 4 years ago, and the idea was, as we'll talk about the next time, there are advantages to observing in the infrared part of the spectrum rather than the optical or visible part of the spectrum.
Yeah.
If you want to look through dust, or if you want to look at the early universe, because light coming from the early universe, as observed by us, appears to be redder than it would if it were nearby. And so after Hubble, they wanted to build a bigger telescope. Hubble is a 2.4-meter telescope. JWST is 6.5 meters. They also decided to focus it on to build cameras that observed in the infrared so they could detect more galaxies in the early universe. And it really is an amazing device. It works better than predicted. And everyone is very excited about it. And so NASA, even if things are really bad at NASA, they will keep JWST going. And Hubble has some issues with it's the fact that its instrumentation is getting old. But they'll keep it going because it's still very productive.
Thank you.
Okay, well, I think that was wonderful. I do feel a little paranoid about this idea of having Zoom outages and tornado warnings and things like that. But apparently we didn't, maybe the next time there'll be a supernova in the middle of my talk, but I hope not. Okay,
Thank you, Martha.
all
Thank you
right.
so
Thank
much.
Bye-bye,
you.
everybody.
Bye.
Bye, everybody.